Okay, so we were discussing latches, right? And we were discussing the concept of, we started the idea of time borrowing, but we really did not derive any condition for that. But before that, let us just revisit what we did last class, but this time with a slightly different clock waveform. Let us assume that the non-overlap period is actually very small, because that's why it was not evident again that there would be a hold time violation, because there was a long gap, right? Non-overlapping clocks give you that advantage. You will never have a hold time violation because that non-overlapping time is large. But suppose that were not the case, then we will see what happens today, right? So let us just revisit the latches max delay and min delay constraints. Okay, so what is my constraint? Okay, let me just go to the new page because I need more space. Okay, I have latch L1, combinational block C1, L2, combinational block C2. Now instead of going to L3, I am going to bring back L1. Okay, physically in space this is not L1. I am actually unrolling this in time. So that's why I am saying you look at L1 again at that particular edge. Okay, ideally I would have had L1, C1, L2, C2, then L3, C3, L4, C4. There will be different blocks, right, physically in space. But now I am trying to consider what happens into L1 at a different time instant. Okay, so I am unrolling this in time, not in space. Okay, so this will be back to C1 and L2, C2. Okay, so my clock phi 1, phi 2, phi 1, phi 2. Okay, so let us look at phi 1 here. I am going to have a rather long period, okay, so that the non-overlap period is very small, just so that you get a clear picture of why there is going to be a hold time violation. Phi 2, again both latches are positive latches. Okay, so what is going to happen here? This is going to rise somewhere here, right? And so on, right? So now what is my non-overlap period? It is basically this period, right? This is T non-overlap. Okay, and of course from this rising edge to this rising edge is my clock period itself. Phi 1 rising edge to the next rising edge is the clock period itself. Okay, so now what happens is I have data D1, Q1, D2, Q2. This is D3, and now I am coming back to L1. Okay, so physically that's not the case, so I will not worry about labeling that for now. Okay, we'll come back to it when we deal with the min delay constraint. Okay, so now what is going to happen? I am going to have a change in D1 that needs to be captured, and before we proceed, let's mark our violation window very clearly, right? This is my violation window for phi 1. Falling edge is when it is going to sample the data and it has to hold that data until the next rising edge, right? Until the next data comes. That's the point. If it does not hold it, there's a violation, right? Similarly for phi 2, this is my violation window. Okay, phi 1 again I have a violation window here, phi 2 this is my violation window. Okay, so I am going to have a change in D1 like this. D1. Okay, it has changed and it has given rise to event 1 that all these blocks need to process. So the event 1 has changed, L1 will capture it, hold it, C1 will process that, then it will go to D2, D2 will then get sampled by L2, it will hold it and that has to proceed. That event 1 has to be processed by each and every latch and combinational block appropriately. Okay, so now what will happen to Q1? If you look at Q1, where will it change? Or what is the delay it will incur? TDQ, right? Because I am saying that in a latch, data does not have to change exactly before the rising edge. It can change even afterwards. Remember, the latch has to hold event 1, right? And just hold it till the next rising edge. For that, the data has to settle before event 1 has to settle before this violation window. That's all. I'll call the violation windows V1, V2, V3, V4. Event 1 has to settle before violation window V1. Then it will get sampled correctly. There is no problem. Okay. So what will happen to Q1? Q1 is, there will be some small variation of course, or some small contamination delay. Okay, right now we are looking at the propagation delay, so I'm not going to mark the contamination delays, right? So this guy, D to Q, right? This is T, what? T, P, D, Q. T, P, D, Q. Okay? Then what happens to D2? That is going to, again, it will start with some contamination delay. Let me start that delay very early, right? There will be some long thing before the propagation delay actually allows it to settle. Okay, this is more like a realistic picture. The contamination delay can go through C1 very quickly, right? But the propagation delay might still be long and the time to settle may take it well into phi 2. Okay, so this is what? D2. Right? Now what happens to Q2? So it has gone into phi 2. The delay it will incur is what? TDQ again, right? So Q2 is, and of course all this is event 1. Okay. Now, when will the contamination delay start for Q2? Can it start here? What is the contamination delay that Q2 will see? It has to wait until the clock turns on. So therefore, contamination delay can come only from clock to Q. Right? It cannot come from data to Q because the clock is not turned on. Any change here is not going to affect the data there. Correct? Are all of you with me here? That's why for max delay we are considering the data to Q delay, but for hold violation we are considering the clock to Q delay. Okay? Very important this point. So it cannot be this. As soon as the clock changes here, you will find that this can start changing like this. Right? And it will settle after some delay. Okay? Now what are the delays here? From this is what? T, P, D1, right? For combinational block C1, it is TPD1, correct? From here to here, again, what is it? From D2 to Q2, change is what? Delay is T, sorry, this is TPDQ again, right? So this is TPDQ1, or I'll just call it TPDQ, identical flops. Okay, same delays. Now what will happen to D3? Okay, so actually now I am not going to look at D3 here, I am going to look at D1, right? So what do I want? Yeah. So first of all, what is the max delay constraint here? Assuming that I am not going to borrow time, okay? What is time borrowing? If you look at this D2, right? The change has happened well into the rising, the on time of phi 2, okay? This guy, the change here, there has been a significant amount of time borrowing that has happened there, right? You are allowing D2 to settle after the clock has gone high. That is called time borrowing. Okay, we'll see what the condition should be. How much of time I can borrow is also one condition. So we look at what that is, right? How much of time can you borrow in a flop based system? 0. It's a hard edge. If you miss that edge, you have to wait for the next cycle, right? That's the whole advantage of going from a flop based system to a latch based system, because I can borrow time, right? So we'll see some advantages of this very clearly later, okay? So assuming that this has to finish within the clock cycle TC itself, what should be the condition now? So okay, sorry, this is D3. I have to look at D3. I'm sorry. D3. So what will happen to D3 now? So now D3, what is the contamination delay? With respect to what will it start? As soon as Q2 starts changing, it can cause, because it's a combinational block. It has nothing to do with the clock, right? So therefore, this will start changing somewhere here, right? Right, and so this is what? TPD2, correct? So what is the constraint for the max delay? TPD1? What? No. Be very careful. Where is the violation window now? Huh? B2. No. Hold on. D2 is being sampled by phi 2. Correct? Now I am looking at phi 1. Right? D3 is now going to be sampled by phi 1. So therefore, there is no violation window. It's very far away. That's why I am drawing this waveform again specifically. If you draw it with very large non-overlap period, these things may not be obvious. Okay. So therefore, there is really no violation here, violation window. There is a long time. If I have to finish within that cycle, if I can borrow across cycles, then you are right. I have to finish it. I have to finish before violation window V3, not V2 also. Okay. So therefore, I have my clock period TC, and then what should happen? I have my delays TPDQ plus TPD1 plus TPDQ, right? I can call it 1 and 2 actually, not big deal, right? Plus TPD2. And what's the inequality? Greater than or equal to. Clock period should be greater than this. If clock is slow, no problem, it can accommodate it, right? Implies TPD1 plus TPD2 should be less than or equal to TC minus TPDQ1 plus TPDQ2, right? Yeah. No, you're right. I'm saying, of course, if you can borrow time, that's what I said. Borrowing time from phi 2 is time borrowing across half cycle. Borrowing time across a half cycle is always allowed. So that's why we are not worried about restricting it within the half cycle. But time, time borrowing across cycles is prohibited in some cases. I'll show you next. That's why I'm first deriving the condition saying, if I have to finish within the same cycle, then this is the condition. That is the amount of time borrowing. Yes, I'll come to that next. Okay. Okay. So now, when can D1 change? Let's assume that D1 is coming from a primary input where I have control. I will say that, okay, you should not change data in a certain period. So if I want event 1 to be captured, okay, this is event 1. If I want event 1 to be captured, when can D1 now change? Immediately after, now tell me which violation window? After V1. The earliest time that D1 can change successfully without affecting the operation is after D1 has been sampled correctly to Q1. Which means that D1 can now change only somewhere here. So it will change like this. Okay. Then this is event 2. Okay. Now what should happen to this? Let's look at, okay, D1 has come through there. Yeah. So what is the constraint on D2? How long should D2 be stable? Right? What is the job of Q2 first of all? After phi 2 falls, data has to be sampled and it should be held until the next rising edge of phi 2. Correct? The intent is Q2 should remain at event 1 until this period. Correct? Is that right? Correct, right? Okay. So now, in order for that to happen, D2 should be stable for how long? After which violation window? So D2 should be stable until after V2's violation window. Now let's see what happens when event 2 comes in on V1, right? After the violation window V1, no problem. So that has been taken care of. Now, because D2 came here, you look at phi 1 again. Okay, here. Because that's only when phi 1 goes high again, will the change in D1 be allowed to go through to Q1. Correct? So as soon as phi 1 goes high, I am going to have a contamination delay in what? In Q1, right? So therefore, you look at Q1 now. As soon as phi 1 goes high, I will have a contamination delay. This is what? T. Which one? Contamination TCCQ1. Correct? Now, as soon as there is a contamination delay on Q1, it can reach D2 because it's a combinational block. Correct? So, what will happen to D2? D2 will start changing like this. Right? These are actually very small delays. That's why I'm showing it, trying to show it. I'll remove this, okay? Maybe I'll put that here. T, P, D, Q2. This, what is this delay? From Q1 to T2. Huh? T, C, D1. Correct? Now, what is my constraint on D2? D2 has changed. What did we say, or when did we say that D2 is allowed to change so that there is no violation? After violation window, V2. Right? So, this is what happens if data changes and the overlap period is very, very small. Non-overlap period is very small, I'm sorry. Right? If that happens, then this data can race through from D1 to Q1 through C1 and contaminate the data that was supposed to be held by D2 in the earlier cycle. Are you with me? So, what is the constraint for this to work correctly? Huh? T hold is with respect to which clock? Phi 2 now, right? So, from here, I have a hold window, right? This is my, let me do that in red. This is my hold window, correct? Now, what are the delays that I am going to incur? First is the non-overlap from phi 2 to phi 1, right? Because you remember that now the changes that you see in Q1 and D2 are because of the clock phi 1, not phi 2. So, therefore, I have to now go from this edge through this delay, right? Then through this delay. So, I have to count this delay as well. What is that delay? That is the T non-overlap. So, therefore, my min delay constraint is T non-overlap plus T what? CCQ1 plus TCD1, and I have a T hold constraint here. What's the inequality? Less than or equal to. Violation window V2 should be small enough, or the data change in D2 should happen after that, right? Which implies my TCD1 should be greater than or equal to T hold minus T non-overlap minus TCCQ1. Correct? This is my min delay constraint. This is max delay. This is my min delay. Okay. Now this TCD1 that I said, whatever discussion we did, we have to do it even for C2. The same discussion will hold even for the outputs D3. Right? D2 should not race through and cause a change there, everything. So for every latch, I have to do this. correct? So therefore, I will simply say TCD 1, 2, T hold T overlap 1, 2, T hold minus T non overlap minus TCCQ 1, 2, right? Same condition is going to hold there as well, just that the delays might be different. So last time I left you with one question. I said that max delay constraint is one constraint. If you look at this, it is TPD1 plus TPD2 less than or equal to TC minus some two propagation delays, right? So we got one constraint for max delay and one constraint each for min delay within one cycle, that is for the two latches, correct? A flop on the other hand has only two constraints, one max delay, one min delay. Okay, this is for a latch. How does a flop look? By the way, the condition TPD should be less than or equal to TC minus PCQ plus T setup, correct? You remember this condition for the flops? This is what we had. Because we have hard edges, you have to set up before that edge and all that. If you look at the max delay constraint, it's not very different because TPD is the net. Suppose I had implemented this system with a flop. What would I have done? I would have put a flop F1 here, right? And then combine the block C1 plus C2 and then put another flop here. So this would have been 5, 5. So if you look at the constraint here, it's not very different. TPD is less or equal to TC minus TPCQ plus T setup. For a latch, it is this anyway is actually TPD, and the TC sequencing override is what? TPDQ plus 1 plus TPDQ2. If you look at it, if you remember what we derived earlier, the TPCQ and T setup are nothing but the TPDQ and TPDQ, of L1 and L2 separately. So this is not very different. The max delay constraints are almost identical. It is clock period minus 2 latch delays. In a flop, we call it TPCQ and T setup. In a latch, it is just PDQ1 and PDQ2. So it's not very different. The min delay constraint, however, is different. We are getting two conditions as opposed to a single condition which was TCD should be greater than T hold minus what? TCCQ. Right? That's what we got there. But where did that third condition vanish? Because a flop, after all, is just two back-to-back latches. We have taken that latch out and put it somewhere in between, split that combinational block which was C1 plus C2 and made it C1, C2 and inserted that L2 here. How did the third condition come in suddenly, which was not there earlier? Yeah? Correct. That's because you have control on C1 and C2. No. My question is, did the condition really get removed at all? Ah. T hold is okay. So what I'm asking is, basically now you have in the latch system, I have one min delay constraint per latch. per latch. In the flop, there magically seems to be only one min delay constraint for the input flop, input latch, L1. Where did the condition on L2 go? So the answer is the condition did not vanish. If you remember, that condition was a function of the delay of the latch inverters. You remember when we did this hold violation analysis, the 1-1 overlap which happened on the non-sampling edge, you had to ensure that that delay was less than the propagation delay from input to that second latch. And if you violated that, your flop is gone. You will have a hold violation or a race condition. So that condition is implicitly there in the flop design. The difference in a latch based design is I have control now over even that delay, because I can design C1 and C2 to make sure that delay violation doesn't happen. In the flop, if you had that violation, then you're gone, right? Let me show you that, right? We had that. You see this? Yeah. This was the non-sampling edge. This is a negative thing, right? This non-sampling edge, because of the overlap, had to have some constraint there. And what was the constraint? It basically said that the overlap period should be smaller than the delay of going through this pass transistor, through this inverter, through this pass transistor, and getting there. That was an implicit condition in the flop design. So it's not that the condition vanished. The condition is implicitly there. There are still three conditions, but one is something a designer does not have control over. It has to be taken care of at design time of the flop itself. If I give you the flop, that internal race condition constraint is already fixed. You can do nothing about it. Whereas if in a latch based system, I can do something about it because C1 and C2 are still in my control. Okay? Clear? Please think about this. It's a subtle point. Think about it and you see what happens. Okay, now what happens if I have clock skew to these two conditions? Right? What happens if I have clock skew? Right? I'm going to have this sampling edge. Right? So will the max delay constraint get affected? Will the max delay constraint get affected if I have clock skew? So you might think that if I want to finish it within that cycle, then it will get affected because the clock edge moves, right? But I'll show you later that that's not a constraint, because if I want to finish it within one cycle, it's only when I have feedback, which means there is no skew because I'm now dealing with the same flop again. Okay, I'll show you where that thing will not. So in general, this is skew tolerant. The reason is, if I have a subsequent block L3, L4 and so on, then technically I can borrow some time from the neighboring clock period also. So there's no need that it has to finish in that one time period. Okay, if I can borrow. So therefore, even if that edge moves a little bit, I am still okay. So in general, latches are skew tolerant, okay, for max delay. However, min delay, that's not true, because like I showed you last class, this will become Q plus this. Why? Because now my hold constraint is going to happen with respect to the clock that moves this way. Phi 2 will move to the right a little bit. and therefore I have to ensure that the hold constraint is with respect to the shifted clock. So T hold plus T skew will come in there and it will alter all this condition here. So this will become T skew plus T hold plus whatever. Yeah. No, again, see, the thing is T non-overlap is a design parameter. T skew is something that comes in post because of manufacturing. So you can't combine it. So the thing is T skew is variable. Okay, in the sense T non-overlap is fixed for all clocks everywhere in the system. Whereas T skew, the worst case, right, is actually like a random variable. On this part of the chip, it may be some value. On that part of the chip, it may be some other. So I cannot combine it with a design parameter which is supposed to be a fixed number. Okay. So how much of time can I borrow? How much of time can I borrow? Oh, before that, by the way, let me show you this. Okay. The book, textbook Weston Harris discusses this min delay constraint slightly differently. Look at this. If you look at the diagram here, the way the book does it is time is what is represented here. So if L1 is ahead of L2, it means I am looking at the previous cycle of L2. That's why my L1 and L2 is not drawn in a straight line, because that represents the physical picture. L1 and L2 are going like this, L1, L2, L3, L4 will go like that. So time also proceeds in the same direction. The reason he has sort of brought it back like this is to show that they are both dealing with the same event. I unrolled it in time and drew it on the same, on a continuous thing. That's why. Whereas the textbook has drawn it like this, and my slides also has it like this. So if you unroll this in time, then this guy will become straight here. That's how. So that's how you have to tie the what I have done in class and what's on the slides and in the textbook. Okay, this is just a notation and a style of showing it. Okay, both are equally valid. This unrolling seems more easy to explain. That's why I am doing it like this. Okay.